Hello everyone. Today we're going to continue on our discussion on lines and plane, mainly in parametric form, but we will also talk about how would they look like in standard in equation form, which you already know about lines. So yesterday, the last example that we did, we talked about how to write a parametric representation of a line. If I give you the direction vector and a point on the line. So pretty straightforward. And when we finish, we realize that, and I show you that you can actually write out this line in the following three ways right here. So I want to kind of tell you what they are. So the first one is the following. So I have this one line right here. So first representation is this one, vector x equal to t times 1 comma 2 plus 3 comma 4. So this is often referred to as a parametric representation. In this expression, vector x represents all the variables involved. In this case, there are two. And the reason why I know there are two, because I look at these two vectors, and these two vectors have two numbers in it, represented in R2, and therefore vector x has to be in R2 also. And it's called parametric form because you have t, which is the parameter. So another way to write that is to write it this way instead, which you probably remember writing it from last year. Which is how last year, when you learn about parametric curve, that's how you learn it. One way is to write it as two separate equations like this. Or in some cases, you see it written this way. So this, I'm going to refer to this as the vector form. Because you actually write it kind of like a vector. Okay? And some of you probably remember learning it this way from last year when you learned about parametric curve. And in this way, it's making it easier for you to generate the value and to plot on the graph. So it's more easier if you put it into this form so they can draw the graph. While in parametric form, it's probably easier if you're working with vectors and more algebraically have to manipulate the expression. While in vector form, it's more likely that you can use that to actually see what the graph look like. And now, of course, we have this form right here, which is y equal to 2x minus 2. So that's, I'm going to go ahead and refer to that as the equation form. Which does not involve the parameter t, and simply just show the relationship between x and y. All these three ways to represent is to represent the same thing, a line. Just basically the way you describe it being different. So in the parametric form, you basically describe the line by first having a point of reference, or quote-unquote starting point, which is 3, 4. And then you're allowed to go in either the direction of 1, 2 or the opposite direction of 1, 2. And that gives you the line. And in vector form, you basically have two equations to define x and y, and then you can simply just plug in different value of t to generate a table for your line. And then in the equation form, you're basically just describing a line through the slope and the y-intercept. So if you think about it, the parametric form and the equation form are actually quite similar, because in this sense, you can think of the slope being like the direction vector, and then the y-intercept would be the point on the line. Now, however, something very important that I want to demonstrate to you about parametric form that you need to make aware of. So to illustrate that, I'm going to show you a very simple example. Suppose, let's say we're given an equation of a line, how to rewrite it. Oops. In parametric form. In parametric representation. So in our last example, I kind of show you how to write it from parametric to regular equation form. You can simply do that by just looking at it from a graphical standpoint and identify what the slope and the y-intercept is. If you draw your graph, you should be able to trace it out. And if not, you can also try to manipulate the equation in such a way so that you can solve for the equation x and y. And it can be done quite easily for a line. It will get a lot harder when we have more variables involved. And when we get to that, I'll show you. So, but here we're asking for the reverse process. Suppose I have an equation in y equal mx plus b form, an equation form. How do I write it into parametric form? So show you a very simple idea to do that. So let's say, for example, I'm going to let y equal to, I don't know, 3x minus 2. So very nice and easy equation. So how can I write in parametric form? So what you have to do is understand what does it mean by in parametric form. So in parametric form, two things must happen in order for us to put this equation into parametric form. So first, this equation right now as it is written show a relationship between x and y, where x changes y in this case, because the way the equation is written, it indicated x being the independent variable and y being the dependent variable. So when I change x, y changes along with it. What we need to do to put in a parametric form is to somehow do the following two things. Number one, introduce new variables called parameters. And number two, somehow rewrite all the variables, which in this case x and y, in their own equation in terms of the parameters. So for a line, I'm going to show a very simple process. For a line, based on what we have seen from what is this basic parametric representation of a line, which is right here, you see that we need only one single parameter to do it. One single parameter, which we're going to call t. So that's what we're going to do. I'm going to create a new parameter for this equation. That way I can use that to write this in parametric form. So how? Well, guess what? You actually have the freedom to do whatever you want, to choose to however you want to choose the parameter to be. And because we probably want to simplify the process and make the process as easy as possible, this is what we're going to do it. We go let's y equal m 3x minus 2. Let's rewrite in parametric representation. Oops. So this process basically requires you to create a parameter and then try to use it to represent both x and y with it. So the easy way to do is the following. We just go and say, well, how about we just let x become our parameter t? And if I do that, then our y would be 3x minus 2, which just turn into y equal to 3t minus 2. And guess what? We accomplished what we want to do. We have x in terms of t and y in terms of t. That's what we need to form a parametric representation. So now what we have is this. Now what we have is this equation, x equal to t, y equal to 3t minus 2, or in vector form, t, 3t minus 2. Now, here comes another important step that you need to know. So now, how do I write it in a parametric representation? So this is good. This shows a vector form of our line. And it's pretty easy. You just basically let x equal to t. Or in this case, the easiest way, something worth writing down for yourself, the easiest way to rewrite an equation into a parametric representation is to kind of pick the independent variable to be the parameter, because if you think about it, it makes sense. The parameter basically serves the role of an independent variable, but we just can't call independent variable because they don't appear on the graph. So we cannot call them a variable. So in this case, the easiest way to make x, which is our independent variable, to become a parameter. Then I can just simply rewrite everything in terms of the parameter and be done with it. So now here comes an important step, and you will use this concept a lot for the rest of chapter 1 as well as chapter 2. and also if you're junior this year, next year in differential equation. So make sure you understand the concept. So now what I want to do is rewrite into parametric representation, which will require me to define a direction vector and a position vector. So show you how that is done. And it's actually quite easy to do. All you really have to do is to learn to line things up properly. So I'm going to say x is equal to t, and y is equal to 3t minus 2. So notice that I line up the t, and I kind of line up this part right here. And now all you have to do is learn to fill in things that they're there, but just not written out because we don't write them. And that will be the 1 in front of the t. We usually don't write the 1 in front of the t because understood is there. 2, I say 1 t, but there's no number at the end, meaning it's effectively plus 0. And now something very important I want to make sure that you do, because otherwise you'll get it wrong. What you want to do is see this minus 2 right here on the bottom. You don't want to do subtraction. You don't want to do minus 2. Reason? Because we only define vector addition. So what I'm going to do is I'm going to go and change this to a plus and put a minus 2, put a negative 2 right here. And now to actually write them into vector form, all I'm going to do is group these two numbers together and these two numbers together, and voila. Oh, actually, and I'm going to also group the x and y together, and voila, I can now put into vector parametric representation. Vector xy is equal to t multiplied by the vector 1, 3 plus the vector 0, negative 2. And when you write in this form, notice that now this becomes our direction vector, which I believe we call vector u. And this become our position vector, which I believe we call vector v. Now, very important that you have this plus sign right here. This right here cannot be a subtraction. I repeat, it cannot be a subtraction. The reason why it cannot be a subtraction, because if it is a subtraction, it will mess up your position vector to a different location, and therefore screw up your definition right here, because you will need the position vector to be on the line. So if you make the opposite of this point, that point is not going to be on the line, because it will actually be further down on, in this picture, negative v will be like on this side right here, which would not be on the line at all. So you don't want that to happen. So this sign right here must be a plus sign. So what happens if there's negative? When you write it out like this, well, the negative will go inside the vector. That's how you do it. So if, like, let's say both the top number and bottom number are subtracting, you basically still put plus, but you just make these two numbers negative. All right? Important because of the following. Okay, this vector right here represents a position on the line, and therefore if you take x to be 0, y to be negative 2, and you plug it into the equation given to you, it should satisfy it. But if you put a minus right here, then now all of a sudden you have 0, positive 2, and when you plug these two things into here, the equation is not satisfied. It doesn't work. That's the reason why this has to be a plus sign. Do not ever put a minus sign right here. It would be t vector u plus vector v, not minus. Never. All right? And in this expression right here, this would be a point on the line which referred to as the reference point. And this would be the direction. Now, that seems like very easy to do, and as a matter of fact, you're correct. It is very easy to do. Just simply pick the independent variable as the new parameter, then everything just works out perfectly. Well, I hate to tell you, but there is an issue. So what's the issue? The issue is the way we write this particular parametric representation rests on the fact that we choose x to be t. That's a conscious choice that we made. And Therefore come the question, is that the only choice that we can make? And the answer, no. As I told you, you can pretty much create the perimeter in any way you want. So what could be some other choices, and what would be the consequences of choosing differently? Well, let me show you. Suppose we have the same exact problem. Let's say we're given y equal to 3x minus 2, and we also want to rewrite it in parametric form, in parametric representation. So we can definitely just let x equal to t and just be done with it. And as a matter of fact, that takes quite little effort to do that. But what if I don't want to do that? What if I do this instead? Imagine I do this instead. Let's say I'm going to let y equal to t instead, which is perfectly fine. There are two variables in the problem. I mean, you know, some of you might like x, but what if I like y better and I want y to be my perimeter? Well, then this is what happened to the equation. Then t would equal to 3x minus 2. And then after some algebra, you can once again pause the video. If you want to just do them yourself, you should. Try to solve for x. So pause the video, try to solve for x. Once you're done, put it back on. And if you solve for x correctly, x would equal to 1/3 t plus 2y. So what happened to my equation now? Well, it become this. Now, important, even though we did let y equal to t, but when we list them as in vector form, it's always x comma y. It doesn't matter which one we do first. Okay, so therefore in vector form, this is 1/3 t plus 2/3 t. Notice that is quite different compared to our last answer. And so now what I'm going to ask you to do is go ahead and go through the process of writing into parametric representation and identify the direction and the position vector. Okay, so tell me to pause the video and go and do that. And once you're done, you can go back on and see how I do it. Okay, so I'm going to go ahead and do it because you can pause the video. So if I go ahead and do this, I'm going to say x equal to 1/3 t plus 2/3. And y is equal to t. So I'm going to do the same thing like last time. I'm going to put a 1 right here. I'm going to say it's plus 0. And then we'll group them together into vector form. And then we'll say, well, that just means we have xy equal to t times 1/3 1 plus 2/3 0. So this is my vector u and this is my vector v. Uh-oh, now we have a problem. The problem is this answer doesn't look like my last answer. And so what's happening here? Is only one of them is correct? Are they both correct? What's going on? So here comes a very important concept that you need to understand. And students often don't get this and always get confused about it. And the concept is this. Parametric representation, no matter what we use to represent it, but parametric representation of a line is not unique. Meaning the following, meaning that this line, if I describe it as an equation, the only equation that we'll be using is this one. Y equals 3x minus 2. There's really no other equation. If I give you a different equation with a different number, like not the 3 or not the minus 2, it would always represent a different line. Okay? But in parametric representation, it's quite different. We just found two different parametric representation. One is right here, this one right here, and one is right here. And guess what? They both represent the same line. Well, how do I know they both represent the same line? Well, it's actually not that easy to tell by just looking at it, but for a line, it's actually not that hard to do, and I will show you how. But the important concept I want to get across right now is that parametric representation is not unique. Therefore, it's entirely possible that if I give all of you an equation of a line in y equal to mx plus b form, and ask all of you to rewrite it into parametric representation, and I could theoretically get 10, 15, even as many different answers as the number of students in class. It's possible because all of you choose to do a different thing and therefore result in a different parametric representation. But they could all be correct. So question comes down to, how do I know my answer is correct? I mean, let's say your classmate next to you do it one way, but you do a different way, and now you compare your answer and like, oh my god, they don't look the same. Now what? So, and how to tell whether they're the same or not is actually using a fact that you learn in geometry to do it. In geometry, you learned that if two lines are parallel to each other and intercept each other, they must be the same line. So that's how we could determine or show why these two parametric representations are actually the same. So this is how. So several important concepts that you have to write it down for yourself. Okay, how do I tell two lines are parallel in parametric form? Two lines are parallel if this is true. If their direction vectors are multiple of each other. Okay, if the direction vector are multiple of each other, then the two lines must be parallel. So in our case, we have these two parametric representation. I forgot. 0, -2. And this parametric representation. Okay. So this statement basically states that if the direction vector are multiple of each other, they have to be parallel. Now, why is that the case? Well, if you think about it, it makes sense. Because remember, every direction vector defines basically two things: a direction and a magnitude. And we already established from yesterday's video, the magnitude of your direction vector doesn't really matter because it would still be on the line, but just how long your direction vector is. And we're going to multiply this direction vector by a scalar, the perimeter t, to stretch it out anyway. So therefore, it really doesn't matter that much what the how long the direction vector is. It does have significance that we'll talk about in chapter 4, but for us right now, it doesn't. So therefore, if you think about it, if two direction vectors are multiple of each other, what does that imply? Well, based on what you learned in 1.2, multiple of each other meaning scalar multiplication, and scalar multiplication does not change direction, only the length. So therefore, if these two direction vectors are multiple of each other, that means that they still go in the same direction, just one is probably longer than the other one. So in this case, you can see that it totally is the case, because if you look at it, you can see that 1/3 is basically equal to 1, 3 is basically equal to 1/3 of I'm sorry, backward I have it. 1/3 is basically equal to 3 times 1/3, 1. So the two direction vectors are actually multiple. One is 3 times longer than the other one. So therefore, tell me that these two lines must be parallel. Oops. And now, a second concept. If two lines are parallel and they have at least one point in common, then they are the same line. So now we just show that these two parametric representations are parallel. So now how do I convince that they do actually represent the same line? Well, by simply showing that they have at least one point in common. So how do I do that? Well, I can easily do the following. If I look at the first parametric representation right here, I can identify that one point is 0, -2, right there. Okay? And all I have to show is that this line can also be equal to 0, -2. Then they would have a point in common. So how do I do that? So here on the first equation, if I have x equal to 0, then xy equal to t times 1, 3 plus 0, -2 will yield xy equal to 0, -2 for this equation. But at a different t value, and you can verify that if you want. If I look at t equal to let's see, -2 instead, then my equation xy equal to t times 1/3 1 plus 2/3 0 will yield xy equal to 0, -2. So now it shows that at two different t value, these two lines actually do intercept. So therefore they must be the same line. Okay. Now, this is where students often get confused. Like, how is that possible? So the best way to actually explain this is to think of it as you're moving. Imagine you have a long straight track that you run on. Okay, instead of like a normal track that go in circle, because that way you can run forever. But let's say you have an infinitely long straight track that you run on. Okay, and imagine you and your friend are both running on this track. Good. And is it possible for both of you to pass through the same point on the track? Of course it's possible, because you both run on the same track. But doesn't necessarily mean that you two will be at the same point on the track at the same time, which is basically what this is describing. This is describing that both representation will actually get to the point 0, -1. The only difference is one representation will get to that point at t equal to 0, and one will actually get to a point at -2. And so how does it look like on a graph? So I'll show you. So let's say here's my line. And no, it doesn't represent that line, but just want to draw horizontal so that easier for you to see. So for like the first line, I'm going to go ahead and label this one, let's say representation number 1. And I'm going to use a different color for representation number 2. So show you how this works. So both of them describe the same line, but just describe it differently. So one of them described the line this way. One of them described that this is my reference point, 0, -2. And it's going this direction, which is the direction vector 1, 3. So this is my direction vector, which I'm going to call this like vector u1, and this is vector v1. And then I'm going to go and call this one with a vector u2 and a vector v2 to indicate they're different. So this is vector u1, and this is the position vector, vector v1. So therefore, now when you describe it using the representation 1, what you're basically doing is using this direction vector as like steps. So you're basically describing, oh, this line will be going like this. So this is like t equal to 1. This is like t equal to 2. This is like t equal to 3. And then the same length will be t equal to 4, and so on and so forth. And then if I go backward, which is perfectly fine, you have what? T equal to -1, t equal to -2, and so on. Okay, as a matter of fact, I'm going to do this right here. I'm going to go ahead and erase the V. I'm going to put it on top, so that way I can use the bottom for representation too. So this is vector V, which is 0, -2. Okay, so that's how this representation works. It's basically kind of, if you think about it this way, you can think of it as like you walking on a straight line, and you start at the position 0, -2, and your steps, how big you walk, how big a step you take, each step will represent by the vector 1, 3. So you can basically count off t equal to 1 is like one step, and then you take a second step, a third step, a fourth step, and on. And of course, realistically, you can take a half of a step or 1/10 of a step. So that's basically changing what the t is. So that's one way to look at it. Now, what happened is the second representation also described this line, but in completely different way. So how does the second one work? Well, the second one defined a different point. Oh, I forgot a subscript here. Okay, there you go. So it defined a completely different point. This is my V2, which is 2/3, 0. And then define a very different direction vector. And its direction vector might be this one right here, which is vector U2. And notice that it's significantly shorter than U1, because U1 is 3 times the length of U2. And then this basically do the same thing. So this is like t equal to, t equal to 1, and then it will go the same length, t equal to 2, t equal to 3, t equal to 4, t equal to 5, and on. So this is like t equal to 3, t equal to 4, t equal to 5. There's a t equal to 2 right here, but I just couldn't get to it. And then I go backward, okay, t equal to -1, and then t equal to -2, and then maybe t equal to -3. So in a sense, both of these representations basically describing the same line, but just with different direction vector and position vector. One way to interpret it is, imagine, just like what I said, imagine you're running on a track, and there are multiple runners on the same track. So if you map out the path that they take, the track would be exactly the same, but their movement would be different. As a matter of fact, a parametric representation is better think of not as an object, but as a movement along that geometrical object. Like in this case, a parametric representation of a line, don't think of it as a line, but rather think of it as some object. You can think of it as a person, most I would say a particle, moving along this line. And this description would now much better in describing movement along the line than an object. And of course, some of you are probably thinking like, that's the reason why you learn vectors in physics. Because in physics, you're talking about object moving most of the time, especially when you're learning about Newton's law of motions. And that's why you use vectors to describe it, because that parametric representation using vectors describe movement better than a geometrical interpretation which just describes the object as a stationary object. Unfortunately, my time is up for today. Well, it's 33 minutes long already, so I'm going to stop right here, and I'll talk to you again tomorrow. Okay? Bye.